Hi guys, thank you for joining. This is the Oracle Machine Learning Office Hours Ask Tom session. Today we're going to have a session for the machine learning concepts, the best practices when using machine learning regression metrics. And Jie Liu, data scientist in our group, is going to be presenting. And Marcos and Asibia, myself, and Sherry, both of us are going to be supporting any chat questions you guys might have. So if you have any questions, please type them in the Q&A session, and then we're going to be able to answer any questions there. So next slide, G, please. So topics for today, we're going to just talk briefly about the upcoming sessions, and then we're going to go through G's session. And at the end, we have time for Q&A as well. So any questions we might not have answered using the Q&A chat feature of Zoom, we're going to take them directly at the end. So for the upcoming sessions, we're going to start a series of follow-along reviews of our example template notebooks every week. So for what we're going to do is every week we're going to do a one subject, and they will be hands-on, right? Because we're going to be using the template notebooks that come with the tool, right? With the autonomous database and with OML UI there. Then while we're presenting and we're going to be talking about all of these topics, you guys are going to be able to follow along and see exactly what we're doing and follow and execute and things along those lines, right? So those are the subjects we have identified as you know, a beginning of that process, right? Now, there's also another interesting session coming up. That's the Oracle Database World. That's on December 1st and December 2nd for the JPAC. So that's a Singapore time zone. So if you guys are in JPAC, right, or maybe you like to watch you know, these late at night, that might be a good alternative. So there are at least 2 hands-on sessions. We have like 3 different sessions that are presenting. On-demand sessions that you guys can watch, but also we have 2 hands-on sessions there. One of them is the Python, the updated Python hands-on session. And also coming in early 22, we are going to do a Python hands-on lab in Spanish, also another one in Portuguese, and then we're going to actually extend the hands-on labs that we have for Python to include AutoML UI and also to include OML services. And we also wanted to start a 101, just like we did, you know, probably more than a year ago now, that we did for different components, classification, regression, but we wanted to do them and convert them into hands-on labs, right? So that not only you guys would understand the concepts and, you know, learn about it, but also be able to use them and do it, you know, side by side while we're doing it. Okay. So anyway, I really appreciate you guys coming, and thank you very much, G, for joining us and doing this session. And the floor is yours.
Thank you, Marcos. Thank you everyone for attending the session. I'm Jie Liu. I'm the data scientist with the Oracle Machine Learning. Today I will cover the regression metrics in OML for Pi. As usual, I will start with you know, some theory, some of the theories, and then we will go through when to use which kind of metrics in practice. And then I will go to the demo section and show some demo notebooks. So the main motivation is we probably have seen a lot of regression problems when we do the data science practice. Always the question, you know, after we fit a regression model, how we can evaluate the performance of the model. So there are a couple of ways we can either plot the results, at least 2 kinds of a plot, and also we can calculate some metrics which give us one number to evaluate the performance. So the first I will quickly go through some plots we are often using for example, like we are given a data set that contains some demographic features of a customer, So we want to build a model to predict the customer's income. So we go ahead and build a model, use whatever method we like. And then the question is, how can you evaluate your model? The very straightforward way is that you can plot the quantity you want to predict and the prediction. So here the quantity you want to predict is the income and your prediction for each corresponding ground truth. So you can plot them in one 2D plane. And ideally, if you achieve a perfect prediction, so all the points should be distributed along this this line, like the tangent equal to one line. And we can see here in this example, we can see this model doing a very decent job. We can only see a few lines just drift away, but most of them are distributed along this line. So this gives us a very straightforward way to evaluate, to get a sense of how performance of the model is, and it's very intuitive. But the problem is not always we are lucky to have a very a moderate size of data set to allow you to plot this, generate the plot. You probably need to sample, doing some massive work when the data set is large. But most trouble is you can imagine every model will come with different type of image or plot. How can you tell the difference? How can you compare with different models? So that's the drawback. But anyway, this plot is kind of intuitive, and you can definitely try after you build a model and want to get a sense of how it looks. Another plot is very interesting, what we call the residual plot. If you can think about it, we can plot the prediction on x-axis, like here is what we call fitted, and then we can plot the error on the y-axis. The assumption, if you can recall the assumption of the linear regression, we will assume that the actual value y consists of two parts. One part is something you can predict using all the feature, and the other part is the uncertainty. The uncertainty, which is the error. Ideally, if we fit a perfect model, so we will imagine that this error will be kind of independent with the predictions. So ideally, if you plot the residual plot, you will see this error will distribute almost with zero mean and probably with equal variance. It's like on every point they will have roughly the same range. So that means we will have done a great job, because all the model captures the structure of the ground truth, and what left is just uncertainty. That's ideally the residual, which is error. But things are not that ideal usually. Oftentimes we see some other behaviors like what we call the heteroscedasticity. So this is very hard to pronounce, but the idea is sometimes we'll see the variance will keep increasing, decreasing, or in another pattern, the variance will change. So that means inherently the error or your uncertainty is not the assumption is violated. Actually, you probably need to maybe find another way to maybe look for other modeling method, try to capture that. And also there another pattern called the non-linearity, which is often showed up, and you can see that sometimes the error will have some patterns. That means you simply didn't capture didn't get enough features, so that the error still have the residual error. You still have some parts for you to model, but now it's because it's not, you didn't model it, and now you see a pattern here. So this is a very useful part for if you wanted to get a deep dive to see what's left. Can we improve the model? Can we find any way? Can we know that we still need additional feature? So this is a very good way to look at diagnosis the performance. But anyway, this plots for plot-based method, it's like always like you don't have a unified metric, right? You still can't make comparison. So that goes to our metrics. So how we can get a single metric like to evaluate the performance? So one widely used way is called the mean squared error, which is to plot the observed row values and predictions and take squares and then take a mean. So the reason why it takes squares is simply because the error can be positive or negative. If you just sum them up, yeah, probably you will get just cancel them each other. So in order to focus on the magnitude, we take the square and then take the mean. One drawback of this approach is after you take the square, the unit is lost. Like for example, like we want to predict the customer income, the unit is dollar, and if you take a square, so they're not easy to interpret. So the one way is to take the square root, right? To take the square root, you will translate back to the original unit. For example, in our model, you can see directly see that our prediction is like on average we make the error lies in like around $1,000. So this is pretty decent. Like if you want to predict the yearly income for most of people. And there's another way, which is just directly take the absolute value, right? We can keep the original unit and everything is fine. So, but this question is why people come up with this metric and what the difference between the approach of taking squares. So we can do some experiments. If you look at the residual plot, as I mentioned previously, so we can see that in this model, it's like we see several. Yeah, this is definitely like what we call heteroscedasticity. Maybe some around some of the region we are not doing a good job, and we have a lot of outliers here. So we can do some experiments. Like we know that comparing to the entire data size, the outliers is roughly like above like 5,000, and also this is only occupied like 0.5% of the original data set. Let's just directly remove them, right? We remove them and then recalculate the metric to see what will happen. So by removing them, we can see the all the metrics with original data and after we remove the outlier. And we can see that MSE dropped dramatically. Remember, we only remove like 0.5% of the data. But you can see that drops in half, and the RMSE also dropped a lot, like 1/3. This is a lot. And but MAE is like drops by 10%. It's like drops moderately, and the data is still in the roughly the same range. Does that tell us like because of because of the MSE and RMSE, they take square first, right? That means whenever you have something like an outlier, you make a very bad prediction on some of the data points, it will be amplified dramatically in square. So it will a lot of dominant. You can think about the quantity of the MSE will dominated by these outliers. Is that good or bad? But this I would not say it's good or bad, but just depends on the application. So if your business you really care about the peak error, you should use MSE or RMSE because it's directly tells you what will happen. Some dramatic case comes in. If you see some, for example, like we want to do some cloud storage estimation, imagine that the cloud services should be, we should be built a very good cloud services, and we care care about each customer, because cloud is like very essential infrastructure. We can't tolerate even a single customer that have their cloud storage just exploded. in that case, we should use MSE because as long as there are some prediction, one or two single prediction goes way off, that will tell us, that will be reflecting on the number immediately. So that's the right that's the right application if you want to use MSE or RMSE. And when the business goal is does not care about the large error, right? For example, we want to do some marketing campaigns. We want to predict the customer purchasing amount, and as long as we can highlight the customer with a very high life value, maybe lifetime value, that's enough. Like if you can identify some customer who are really a frequent buyer, who will buy a lot, it doesn't matter. Like we will make something way off or not. Because the marketing campaign, we will accept the results. Like we are targeting definitely every time we are doing marketing campaign, we are targeting the wrong people. This does not matter that much. So apart from that metrics, we often see that people are using the R squared and or the adjusted R squared a lot. So these metrics mainly focus on like how your model fits the variance of the data. You can think about like if your data look like this. The best way, to fit the data is like a line with a tangent, maybe like this. The ways to capture this metric is to come up with a baseline model, which here is just to take the mean of all the data points. So this idea is widely used in machine learning. Even when we are doing other data science projects, we definitely wish to come up with a baseline model. Otherwise, you never know your current model is good or bad, or how good it is, or how bad it is. So this metric is in the similar, designed from similar idea. It compares with the average, because the average just to reflect the average of the entire data set. It does not even care about the variance of the data. Right now, if you claim you have a better model, your model should capture the variations, the data patterns. So you just make a comparison here. So here is like 1 minus the all the sum of squares, the ratio of the sum of squares of the error. The fx here is your prediction, and y bar is the average. So you can think about if you make a perfect prediction of your model, and this term will towards 0, and R squared towards 1. And if you have imagine if you have an arbitrarily bad model, then this ratio will be very large, and you will have a negative value. So it's always so just give us some idea, like how and this is the benefit is like it had a range, and it can give you the ideal perfect scenario which the R squared should be. And but then the one problem is like we know that the prediction error always decrease when you have more features added to train the model. So if you want to boost the R squared, then you just keep adding features to make the R squared looks better. But that's not a good practice, because that will leading to overfitting. So in order to also capture that kind of effect, so people come up with adjusted R squares, which is want to punish the number of features they are using. So here we insert this term. Like you can imagine as the number of features goes up, they will punish the this value. So yeah, I think so basically we have an overview of all the theories and concepts. Then we can go to the demos. So this is a notebook I put together. So this shows our example, like our customer insurance lifetime value data set. and we have all the demographic features, and we want to make a prediction on the income. Yeah, we remove some features. Definitely, we are not using like the name. It should be unique in every row. As always, we do the split of the train and test data set. So here, when I build a model, so for demo purposes, I try to, I want to come up with a very good model. So I experiment with different models. So here, what I want to highlight is that if you want to use the GLM, the generalized linear model, when you really want to boost the accuracy, you can add these two options here, like the feature generation and feature selection. This is extremely useful because the linear models only capture, if you just using original features, linear models can't capture the interactions between features. But here, after you add these options, what it does is it will automatically generate the combination of those features. For example, like age, right? Like age, you come up with different interactions, quadratic terms. Yeah, this is age multiply home ownership, all the variations, and it will also do the selection for you. This is pretty powerful. And some in this case, based on my experience, it can even beat the SVM model. So yeah, this is a very good way to want to try. So here we can see that we get some of the statistics. We see just the R square here, which is very high. And the one thing I want to remind you is that this is calculated based on the trained data sets. It's not surprising that we have a very high value. Yeah, this is all the metrics here, R square listed here. But anyway, we need to calculate the metrics on the test data sets instead of the training data set. So if we want to do that, yeah, this is the API score. API will give you the accuracy, and so here you can plug in the text X, text Y. It will also give you the accuracy. This accuracy, yeah, this accuracy is in the classification. The score give you the accuracy, but in the regression it will give you the R square. So this is the coefficients here. Yeah, so the as I said, we want to make predictions on the test data set. This is give us the result. And I put all together the metrics here in one function that we can use the transparent layer. It's pretty straightforward to calculate. So I just calculate by follow the formulas. So we come up with the error and then the square root of error, and then we take the mean. So this is our MSE. And yeah, if we want to, yeah, this is taking an absolute value and also take square root. Also, I come up with the the R square is just the score API, and just R square is just, you can follow this formula. Yeah, so this is give us a list of the metrics here. And you can see when we apply to the test data sets, it's still there are not too many overfitting. The result still looks good. Yeah, this is just a list of all the statistics here. So this is generated the plot I'm showing in the presentation. Yeah, so here it comes with our experiments. So we just remove any all the errors. Remove all the errors above 5,000, and we see how the results looks like. And on the right side, this is the original data. Yeah, so we can see that it's dropped dramatically for MSE, but ME does not drop too much. Yeah, something like that. So you can see how many rows we removed. We just removed a very small portion. So so this is our demo. So I will end here, and thank you very much for your attention. And if you have any questions, let's take some questions from here. Thank you very much.
Thank you, Jie. Thanks a lot. That's excellent. So, guys, feel free to ask any questions. Okay, yes, Suresh. So one of the questions is whether the recording is going to be made available. Yes, that's right. We're going to make the recording of this session available. And the previous session for the classification metrics is also going to be made available probably in the next couple of days as well. That was processing, but it's going to be there as well. So you're going to have both the classification metrics and the regression metrics sessions almost together available. They're asking if the data is going to be made available, Jie.
Yeah, I think the data is just the our customer lifetime value session, lifetime value data set. I think is available in our GitHub.
Right, is available
CSV,
on the GitHub.
Yeah.
Excellent.
Right.
So one thing we can do is you can add actually the command to load the data on your notebook at the beginning.
Yeah.
So that when people download the notebook, they can immediately just run it, right? Because then they can pull the data and then they can work with it. So I think we can make that change. All right. I think that was it. So thank you very much, Jie, for the excellent presentation. And guys, we're going to make the recording available and the notebook available as well. With that change, that makes sure that we pull the data in at the beginning so that you guys can run the example on any of your autonomous database sessions or even an always free session. All right. So thank you very much, and talk to you guys next week. Thank you, Jie.
Thank you. Bye.
Bye.